Hey folks, welcome back. We're talking about dynamics. We're getting ready for exam 3. So this is the chapter 15-16 exam, and we're here to do a practice problem. Along the way, I'm going to be reviewing material. Nothing new, just refreshing, I guess, your memory of where we are. And since this is review, I highly recommend that you pause the video as soon as I explain the problem, attempt to solve it. Since it's review, you should be able to solve it. And if you get to the end of this series and you have managed to solve every problem correctly ahead of me, then you have absolutely nothing to worry about on the exam. So this is our physical system. We have a drum with a brake on it. It has excuse me, the brake has been relaxed and loosened, if you will, and we're told that the block A has dropped 16 feet over the course of 5 seconds. We are advised to assume a uniform acceleration, and we are asked to find A, the angular acceleration of the drum, and B, the angular velocity of the drum at t equals 4 seconds. So looking back at the board, this is the diagram that comes with it, the given statement, find statement. I recommend, pause the video, see if you can solve it. All right, well, welcome back. Let's get to solving this thing. So in this particular problem, there are essentially two key points to remember. One is how constant acceleration affects things, and two is how to convert from linear to radial motion. And so first things first, constant acceleration in the linear frame, right? So we're told that the block A, let's draw it over here, A is going this way, right? And it goes from 0 to 16 at constant acceleration. Well, the formula for that is S equals S naught plus V naught times T plus 1/2 AT squared, right? And every time I see A, I always think about gravity, so that tells me it is time to impose coordinates. So we'll call this X, we'll call this Y, and recall, it's a good idea to stay consistent with the X and Y when we're working with radial coordinates, because things get weird when we do cross products. So in this case, S naught, we can assume that's 0, right? Let's call this 0. Call this time to get a new pen. Alright, so let's see, this guy is 0. We can assume that we were not moving when the system started because there was a brake, right? And and so our motion is downward, right? So minus 16 is equal to 1/2 A, and we're at 5 seconds right here, so 5 squared, right? So that tells us that minus 32, right, and multiply the 2 across, over 25 is equal to A, right? And when we multiply that through, that is 1.707. Wait, I'm sorry, looking at the wrong part of my notes here. This is 1.28. And this is, let's see, those are feet, because this is 0.75 feet, so feet per second squared. Okay, all right, so step 1, step 2, and I should annotate what these are, right? So step 1, find A, right? Step 2 is going to be to find alpha from A. So find alpha, the radial acceleration, from A. All right, and in this case, now keep in mind that A has a radial and a tangential component, but if we were looking here, then radial and tangential component, but since we're looking here, we don't have to worry about it, right? So it's a shortcut, if you will. So alpha, what is alpha? Well, let's see. The formula is A equals R, wait, not R omega, R alpha, right, which comes from the cross product, right? So because we're in plane motion, we don't really have to worry about this because we know the orientation incoming and outgoing, but formally we would think of this as being a, in terms of Cartesian coordinates, alpha is k, and A is, in this case, in the j direction, and then the R we would use in the x direction. So the cross product rules are all still there. It's just that in the simplified example we don't really need it. So when we rearrange this, we get that alpha is equal to A over R, and from the problem statement we know that R is 0.75 feet, so we could say 1.28 divided by 0.75, and that gives us alpha equals 1.707. And then this is radians per second squared, and this is in the positive direction, which is this way. When the problem doesn't give you a coordinate system, it's always best to draw the arrow, just that way you know. So our third step is going to be to find the omega, right? Find omega at t equals 4. Okay, well, again, this is a constant acceleration problem, so the equation that we have for that is that omega equals omega naught plus alpha t, right? We started from rest, so we have these values, so omega equals 1.707 times 4, right? And that gives us that omega, probably make that a little better, omega equals 6.827 radians per second in the anti-clockwise direction. And there you have it. So again, big picture stuff. In this I guess chapter 15, chapter 16, it is critically important to be able to go from radial position or acceleration or velocity to Cartesian, or I guess I would say not Cartesian, but linear velocity and acceleration, right? And as you'll see, most of the problems from these two chapters include quite a bit of that. So anyway, I hope this was helpful, and I will see you in the next video.